Welcome to this video presentation. Let me start by introducing myself. I am JacobKongsted, a professor of chemistry from University of Southern Denmark in Denmark. Now, the title of this presentation here is Polarizable Embedding from Solvents to Heterogeneous Environments. One of the great challenges of quantum chemistry is to be able to design methods that can be used to perform calculations on very large and extended systems, like for example this GFP chromophore here, which consists of around 3,400 atoms. Due to the very steep scaling of the conventional quantum chemistry methods, performing calculations on such biostructures here is not feasible within reasonable time, and we need to design new methods that can be used in order to tackle such calculations in a more effective way. One way of proceeding is to invoke the so-called QM-MM approach, that is a combination of quantum mechanics and molecular mechanics. And this is exemplified here using another protein. This is a PIP protein, the photoactive yellow protein, consisting here of a chromophore and the rest of the protein here. Now, if we are to describe this system here using a QMMM approach, then we would naturally zoom in on the chromophore and treat this chromophore using quantum mechanics, whereas we would treat the rest of the system using molecular mechanics. By invoking such a division here of the total system into one part, a small part that is treated using quantum mechanics, and a large part which is treated using the much more efficient molecular mechanics, then we get a significant speed up in our calculations, meaning that we can really do calculations on such biostructures here. Now, this division here preserves the discrete nature of the whole molecular system, which is in contrast to the use of, for example, dielectric continuum models, and also it is much more focused and of course more effective than use of so-called supermolecular calculations that would take the whole protein into account using any quantum chemical methods. In recent years, we have developed such a QMMM variant, which we call the polarizable embedding model. This is an advanced QMMM model in which we describe the environment by assigning to it a multipole description, meaning that we describe the potential created by the environment by assigning here charges, dipoles, quadrupoles, and so on each atom in the environment and potentially also at each bond midpoint. Now, this gives rise to the so-called static embedding potential created by the permanent charge distribution from the environment acting now at the parts which we treat using quantum mechanics. In addition, this polarizable embedding model also includes induction effects, meaning that we, in addition to these multipole description, also assign polarizabilities at the same sites in the environment, giving rise to induced dipole moments. These induced dipole moments now describe the induced polarization of the environment due to the presence of the QM system. And finally, by including both the static and the induced environmental potential into the one electron part of the QM Hamiltonian, everything is solved in a self-consistent manner, meaning that both the quantum system and the polarizable but classically treated system are both solved using self-consistent field procedures. Now, one of the great advantages of our QMMM method is that we are able not only to calculate ground state properties like structural parameters and energies, but we are able to calculate also excited state and general molecular properties. And we do this through a formulation of quantum mechanical response theory. So basically, this polarizable embedding methodology here gives, through the linear response, access to calculation of excitation energies, transition properties, polarizabilities, nuclear magnetic resonance shielding constants, spin-spin coupling constants, and so on, From the level of quadratic response, we get 2 photon transition probabilities and also excited state properties like excited state dipole moments. Through cubic response, we get 3 photon transition properties and excited state polarizabilities, and so on. Now, all these excited states and also the excited state properties are described through the ground state parameterization, making this implementation here very general and capable of predicting a lot of different molecular properties that can be used to characterize the complex systems that we are interested in. Now, in order to obtain accurate results based on the polarizable embedding strategy, we of course need to use an embedding potential that describes the environmental potential in an accurate way. Generally, we can use, for example, a standard force field parameters like partial charges to represent this embedding potential. But the problem is that these charges have not been determined with the purpose of predicting electronic properties, meaning that they may perform poorly. So the way we proceed is that we do separate QM calculations on a fragmented environment in order to extract the parameters that we need in order to define our embedding potential, that is, the charges, dipoles, quadrupoles, and polarizabilities, and so on, are calculated through ab initio calculations. And let me try here to illustrate this so-called force field hierarchy that we arrive at. If we take a simple environment consisting of a number of water molecules, then each of these water molecules can, to a first approximation, be presented here by assigning only charges. These are calculated using ab initio theory. At the next level, we can also include an isotropic polarizability, including now induction effects in our calculation. We can include an anisotropic polarizability. We can go on and include atomic dipoles and quadrupoles, and we can also go on and include atomic octupoles and have expansion centers also at the bond midpoints. So by this we define such a hierarchy of force field methods that can be used to systematically improve the accuracy of our embedding potential. Looking further here at the electrostatic potential created by these force field methods, we see that going up in the hierarchy, that is going here from a point charge description to including dipoles, to including quadrupoles, to including octupoles, and to including parameters also at the bond midpoint, gives rise to such a reduction here in the arrow between the potential calculated using the force field method and a QM reference. The same is true when we look at the induction part of the induction potential. This figure here shows that the arrow is also reduced systematically when we make a more accurate description of the polarizabilities. Here, using the red curve, we have only isotropic polarizabilities. Using the blue curve, we have anisotropic polarizabilities. And using the orange curve, we have also polarizabilities at the bond midpoints. This increase in the accuracy when moving up the force field hierarchy is of course also reflected in calculations on molecular properties. In this case here, we have been interested in calculating the solvatochromic shifts for acetone and for coumarin, both in aqueous solution. So what we observe here is that performing such calculations of this solvatochromic shift using different force field models indicated here, we see that moving up the force field hierarchy, that is going from charges to dipoles to quadrupoles to octupoles, including polarization here through the isotropic polarizabilities, anisotropic polarizabilities, and also through assigning parameters at the bond midpoint, we finally arrive here at a result which is in very good agreement with the experimental value here. So increasing the accuracy of the embedding potential means that we actually get a much better comparison to the experimental data. Now the same is true here if we look at the more complicated system coumarin. Again, if we neglect polarization, then we undershoot the solvatochromic shift here of around 50%. So the induction part is very important to include. And including this, and especially in the model where we have assigned parameters up to and including quadrupoles with expansions at the atomic sites and also at the bond midpoints, we are able to reproduce the experimental value of the shift in the lowest pi to pi star state to a very high degree of accuracy. In many cases, the environment consists of molecules or units which are covalently bonded together, and in order to be able to treat such systems, we have implemented the molecular fractionation with conjugated caps methods. Now this method is illustrated here in the case of peptides or protein. It basically works the way that you take the whole system and then you chop the system, in this case a peptide, into single residues, and then you use cap groups indicated here with red and blue in order to saturate the free valences. When you then calculate the properties that are to be used for the definition of the embedding potential, then we need to correct for the introduction of those capping groups here by invoking the so-called concap, which is a merge of the two caps that we have used in order to saturate the free valences that would otherwise exist in the two units up here. Even if this way of proceeding is actually quite simple, it actually gives very nice results in terms of accuracy for the embedding potential. So let's look at an example. Here we have the insulin molecule. For this, we have calculated the electrostatic potential on a surface around the insulin molecule using MP2 with a CCPVD basis set. This is our reference value for the potential. This figure up here now shows the comparison between this reference potential and the same potential created by B3LIP, that is a full quantum mechanical calculation. And as can clearly be seen from this figure here, using DFT with the B3LIP functional actually gives rise to quite large arrows in this electrostatic potential here. The reason for this is due to the self-interaction arrow inherent in the B3LIP functional. Shifting now to the molecular fractionation with conjugated cap method here, where we only perform calculations at a single residue at a time, we can see that almost all of the error introduced in the supramolecular calculation up here using DFT now vanishes, and that we are able almost exactly to reproduce the MP2 reference value. So indeed, this method here, the method of molecular fractionation with conjugated caps, works very well in reproducing the embedding potential for such large complex systems. Now, having defined the polarizable embedding method and also an accurate way of calculating the embedding potential, let's try to look at an example where we use this method in order to gain insight into a biological system. This protein here is the so-called photoactive yellow protein, which consists of a small chromophore surrounded by a number of protein residues. When this chromophore here is hit by a blue photon, it should happen now here, it reaches an excited state and undergoes a shift or a change in the conformation, we saw it here, leading now to a change in the overall conformation of the protein, thereby activating this protein here. Experimentally, it has been found that the chromophore exhibits similar absorption properties when the chromophore is found inside the protein and when the chromophore is found in isolation. And we were a bit puzzled about this finding here, because this pointed to, of course, a very weak cofactor protein interaction, and also, if this was the case, that there were this very weak cofactor protein interaction, then there would be no way of performing color tuning of this chromophore when sitting inside the protein. So we wanted to investigate it if it was really true that we had such a small or such a weak cofactor protein interaction that led to almost similar absorption properties of the chromophore in isolation and when inside the protein. So to do so, we first of all tested the expected accuracy of the polarizable embedding model by looking at some small models representing the photoactive yellow protein. Now these small models here consisted of the chromophore and then each residue at a time, that is a residue lying very close to the chromophore. Now for such dimeric systems here, we calculated the lowest excitation energy using a full QM method and using the polarizable embedding method. By comparing these two results here, we could now evaluate the error that we introduced in the calculations by invoking this split of the total system into two parts, that is, one part treated using quantum mechanics and the other part treated using molecular mechanics. And as can be seen here in the error column, we have only very small deviations between the QMMM or the polarizable embedding predictions and the full QM predictions, thereby indeed validating the use of the polarizable embedding model in this case here. Now proceeding to inclusion of the full protein in the calculations. Well, this of course is only doable when we use the polarizable embedding model, and in this case, including the full protein, we got a value for the lowest excitation energy in the chromophore equal to 3.34 electron volts here. Now, removing the protein environment completely, but keeping the geometry of the chromophore as it was sitting inside the protein, now gives an value for the electronic excitation energy equal to 3.24 eV. That is, we have a direct shift or perturbation of the environment, leading to this shift here in the excitation energy of approximately 0.1 eV. Performing next a geometry optimization of the chromophore in isolation and evaluating again the electronic excitation energy gave a value of 3.33 eV, that is almost the same as the value for the excitation energy when the chromophore is sitting inside the protein. So by this we could actually now understand the experimental observation that the chromophore exhibited almost the same absorption properties when in isolation and when sitting inside the protein. And this is simply due to the fact that we have two competing effects, namely a direct effect of the protein on the electronic structure of the chromophore and a geometrical relaxation process when removing the protein or when inserting the chromophore into the protein. And in fact, these two processes shift the electronic excitation energy almost equally, but in two different directions, leading to a total cancellation of these two effects. So indeed it means that there is a potential for performing color tuning of this chromophore here when sitting inside the photoactive yellow protein. There is in fact a shift of around 0.1 eV here caused by the direct perturbation of the protein environment. So by this I will end this short video presentation here of the polarizable embedding model, and I would like to thank the Willum-Fonden, Lundbeck-Fonden, DCSC and the CPR program for financial support making this research possible.